Okay, we're going to do an example now involving an incompressible substance and making use of our incompressible TDS equation that we derived earlier in lecture 25. So the first example involves calculating the minimum amount of work required to cool down a can of soda. And the picture that you have on the screen here, this comes from my book style notes. Actually, in the notes for the lecture, let me go all the way back up. It's this picture. Sorry, having to scroll, but it's this example right here. The only thing different is that here I actually had a picture of a can of soda. This is Werner's ginger soda. I put the picture of Werner's because Werner's is actually a Midwestern soda. This was soda. Werner's is a Michigan-based company originally. And so I thought, we're in Indiana, so let's use something from the Midwest. So Werner's is from the Midwest originally. Anyway, so the goal here is we're trying to find the minimum theoretical work input required to operate a refrigeration cycle to cool down the soda. So we have a soda with a particular volume, 12 fluid ounces. It's 0.354 liters. And we're going to reduce its temperature from room temperature, about 20 degrees C, down to 5 degrees C in a refrigerator. So the refrigerator is operating in a refrigeration cycle. And the way that it works is the refrigeration cycle, the refrigeration cycle pulls heat from the soft drink. You'll see this in a picture I'll draw in just a moment. But there's heat transfer from the soft drink into the refrigerant in the refrigeration cycle. So we're pulling heat from the soft drink, and then we discharge that heat energy to the surroundings, which are at 20 degrees C. So just, for example, through the radiator in the back of your refrigerator out into your kitchen. And what we want to do is find the minimum theoretical work input required to operate the refrigeration cycle. And we're told we can ignore the aluminum can in our calculations. Okay, so what we're trying to do is find the minimum theoretical work input required to operate the refrigeration cycle. So what we're going to actually do is make use of the first law because we're trying to calculate the work input. So let me go ahead and sketch this out for you. Actually, again, it's in my book style notes, so what I'm going to do is just kind of talk through the solution that's already in your notes. So you have to scroll all the way back down. Sorry for doing this. And here we are. So this is the example. This is on page 275 of my book style notes. Okay, so the same problem statement, I just don't have the picture of Werner's here. So first thing we'll do is draw a little schematic of the situation. That's what's drawn here. So what we have is our can of soda right there. And then we have the surroundings. So the can of soda is in our refrigerator. And we have heat going from the can of soda into our refrigeration cycle. So what the refrigeration cycle is, the thing that's in the circle here, these are all the components in our refrigerator that operate our refrigerator. So for example, it contains a compressor, it contains a pump, a throttling valve. It's all of those components are inside that circle there. We don't have to draw all the details to solve this problem, but all of those things that, those various components that we've been analyzing in previous lectures, they're all contained in that refrigeration cycle. So what ends up happening is the energy from the can gets absorbed into the refrigerant inside that refrigeration cycle, like the R134 that's moving around from the compressor to the pump and throttling valve, etc. Right? So that heat is going from the can into the refrigerant that's in the refrigeration cycle, and then we're going to offload the heat from the refrigerant through a radiator in the back of the refrigerator to the surroundings. So that's what the QH is. And in order to do that, of course, we have to put some work into it. This is kind of goes back to the Clausius statement of the second law. You can't just move heat from a cold reservoir to a hot reservoir without doing some work. So we have to put some work into it. So the work here would be the electricity coming from the wall socket when you plug in your refrigerator. So we're going to draw a box. We're going to make our system the can and the refrigeration cycle. Okay, so it's very important to draw your control volumes. Don't forget to do that. It makes a difference on how you analyze the problem. Okay, so we have our control volume drawn around the can and the refrigeration cycle, and there's work coming into the refrigeration cycle and heat going from our control volume out into the surroundings. So what we'll do is we'll apply the first law to that system. So our first law, we've done this many times, just delta E equals Q into the system plus the work done on the system. Here I'm doing work on the system, so I'm using the plus W here. The change in total energy in the system includes the change in total energy of the soda plus the change in total energy of the refrigeration cycle, because they're both contained inside my system or my control volume, so I need to factor in both. The kinetic and potential energy changes are ignored for this situation. Your refrigerator and can aren't falling down the side of a mountain, so their kinetic energies aren't changing, their potential energies aren't changing. So we can ignore any of those changes. So that means that the change in total energy for the soda is equal to the change in internal energy for the soda. And since the refrigeration equipment operates over a cycle, the change in the refrigeration cycle, the change in the total energy of the refrigeration cycle over the cycle is zero, because it's operating on a cycle. So then our first law becomes delta U for the soda equals minus QH. It's minus QH because the heat is going out of our control volume rather than into our control volume, plus the work done on the control volume. And then we'll rearrange to solve for the work, because ultimately we're trying to find the minimum amount of work that we have to put into this system in order to cool down the soda. So we're trying to solve for that work. So now we need to find what the internal energy change is for the soda and also the heat transfer. So let's start with the change in internal energy. Since the soda is a liquid, we can use our incompressible substance model. So here we're going to use the incompressible substance model. So the change in internal energy of the soda is the mass of the soda times its specific heat times the change in the temperature of the soda. So I'm assuming that the specific heat remains constant over the change in temperatures. This is very reasonable since we're only going from 20 degrees Celsius to 5 degrees Celsius. That specific heat would not change very much at all. So that's how we would find the change in internal energy for the soda. So we could substitute that in up there. As far as the mass, that's easy to find. That you can actually find that on the side of the can of soda. The specific heat for the soda, most sodas are basically 99% water, so we'll just use the specific heat for water. And the temperature, the final temperature and the initial temperature, for the soda are given. Final temperature is 5 degrees Celsius. The initial temperature is 20 degrees Celsius. Okay, so the next thing we need to find is the heat transfer, QH. So this is the heat that we have to offload out into the surroundings. So for that, we're going to actually make use of the second law. And the reason I'm doing this is because we're trying to find the minimum amount of work to make this happen. So the minimum amount of work that we'll have to put into this cycle corresponds to one where we would have no internal irreversibilities. Remember, irreversibilities are the non-ideal case. So when you're dealing with internally reversible processes, that's the ideal case. So we're trying to find the minimum work, so I want to think about ideal cases. So that involves the entropy production, because that's where when the entropy production is greater than zero, then you have internal irreversibilities. If it's equal to zero, then it's internally reversible. So when we think about ideal cases, you think about irreversibility or reversibility. That leads you to entropy production, which then leads you to the entropy equation. So that's what this equation is right here. So I said that it's applying the second law, but really I should probably say the entropy equation. It's a better way to state this. So we now write the entropy equation because it's involving this entropy production term, and as I've already discussed. And it involves the heat transfer, because we're trying to find the heat transfer. So the excuse me, the change in entropy for the whole system is equal to the heat transfer that we put into the system divided by the absolute temperature where that heat transfer is occurring. And we're integrating it up over the whole boundary as we go from state 1 to state 2. State 1 is our initial case, and state 2 is our final case. As far as that integral, that we only have one place where heat is coming into or out of our control volume, and that's, let me go back up to the picture, it's right here. Right? So there's only one place where heat transfer is occurring, and that's the heat transfer there is QH. And notice that it's a minus QH down here because the integral is into, but here the heat is actually leaving, so it's a minus QH. And the temperature there we're going to call TH. And that will be the temperature of the surroundings. It's like the temperature where the radiator is on your refrigerator. So it's roughly the same temperature as the room temperature of the surroundings. And then, of course, we have the entropy production. So we can rearrange this equation to solve for the heat transfer. Right? So now we have the heat transfer in terms of entropy production and the change in entropy for the system. And we could substitute that in to our work equation up above. Before we do that, let's talk a little bit about the change in entropy for the system. Just like with the change in internal energy for the system, we have both a component for the soda and one for the refrigeration cycle, because both are inside our system. We have the can of soda and we also have the refrigeration cycle. If we were factoring in the aluminum in the can, then we would also have a term for the aluminum in the can as well. But we're ignoring that for this problem. So we have our change in entropy for the soda and a change in entropy for the refrigeration cycle. The change in entropy for the refrigeration cycle is going to be 0, and that's because we're operating on a cycle. So the property entropy comes right back to its original value. So that's 0. That makes it easy. And the change in entropy for the so then let's go ahead then make use of that. We'll substitute our expression for the internal energy, our expression for the heat transfer back into our first law and simplify that. So that gives us our equation 314 down here. So all I've done is substitute things in there. As far as our change in entropy for the soda, we just talked earlier in lecture 25 about how to find the change in entropy for incompressible substances. Again, we're going to assume that the soda is an incompressible substance. I'm also assuming that the specific heat remains constant with temperature. And so if you go back to our notes for incompressible substances, if you go back to our notes for incompressible substance with constant specific heat, this is how you can calculate our change in entropy for the soda. It's just the mass of the soda times its specific heat times the natural log of the final state temperature divided by the initial state temperature. So we can substitute that in. So that'll go into our delta S for the system. Again, remember that the delta S for the refrigeration cycle is 0 because it operates on a cycle. So let me just focus on this equation for a moment, equation 314. So this is the amount of work that we have to put into our system in order to cool it down. And you'll notice in here that we have the entropy generation term, right? So I'm going to erase some stuff to make it a little cleaner. Okay, so notice that we have this plus TH times the entropy generation, or entropy production, whichever you want to call it. So in order to find the minimum amount of work that we have to put into this, you can see that we would like to have sigma equal to 0. Remember that sigma is either greater than or equal to 0. That's the entropy production. The greater than corresponds to internally irreversible, and the equal corresponds to internally reversible. So to make the work minimum, we would want the sigma to be 0. Of course, it can never be negative because that would violate the second law. We can't have that. So at best, what we want to do is have an internally reversible case. So what we're going to do is we're going to assume, since we're trying to calculate the minimum possible work, we'll assume that this whole process occurs in an internally reversible manner. So we'll set sigma equal to 0. So if we do that, and that'll give us the minimum amount of work. In real life, we'll always have a little bit more work that we have to put into it because it's internally irreversible. But here we're going to try to find the minimum amount of work, so we'll set sigma equal to 0. And so then when we substitute everything in, our minimum amount of work will look like this. So the first term is our change in the internal energy that we found from our incompressible substance model. And then the second term is TH times the change in entropy, again coming from our incompressible substance model. So then we have our minimum amount of work. We can solve for that. So then when you plug in the numbers, we're given that the volume of our soda is 12 fluid ounces, which is just over 1/3 of a liter. The density, since that's volume, so to find the mass, you have to multiply by the density. The density of water is 1,000 kilograms per cubic meter. Soda is, again, about 99% water, so we'll just use the value for the density of water. So we can find the mass of the soda. The specific heat for the soda, again, we're going to assume the specific heat of liquid water. We find that from a table, so you would just look that up in a table. The initial temperature of the soda is 5 degrees C. I'm sorry, that's the final temperature of the soda, 5 degrees C. The initial temperature of the soda is 20 degrees C. And the temperature where we're offloading the heat, we're assuming is the same as the surrounding temperature. This is, again, corresponding to where the radiator is on your refrigerator. So that would be 20 degrees C. I'm converting all of these to Kelvin, and the reason I'm doing that is, first of all, you have to do that when you're taking the natural log here of this ratio. The ratio of, if I used degrees Celsius here, like if I did TF over TI and used degrees Celsius, so this would be like 5 degrees over 20 degrees Celsius. That is not the same as the, 278 Kelvin or over 293 Kelvin. It's not the same. You cannot use degrees Celsius there. You have to use Kelvin. And then certainly the TH has to be in Kelvin. The delta soda, the delta here, that could be in degrees Celsius, because a delta of 15 degrees Celsius is the same as a delta of 15 Kelvin. So that doesn't really matter. But it's always best just to convert it into Kelvin. You'll be safer that way. So when you plug in the values, you can find the change in entropy, for example, of the soda. That's this one right here. Notice that it's negative. The entropy is going down. That's fine. It's totally not a problem. And the reason for that is because there's some heat transfer out of the soda into the refrigeration cycle. If you remember the entropy equation, let me go back up to the entropy equation. Here it is. I'm going to erase some stuff so it's a little cleaner. So if you go back up to the entropy equation, which I'll box in, it's completely fine to have a negative entropy. In order for that to occur, you have to have heat transfer out of your system. So that's fine. We have some heat transfer out, so you can have a negative change in entropy, not a big deal. It's the entropy generation that has to remain equal to 0 or positive. Not the entropy, it's the entropy generation. Okay, so then anyway, you plug in all the values and you can find that the minimum amount of work is just over, it's pretty close to 0.6 kilojoules. So that's the minimum amount of work needed to cool down that soda. That's a useful quantity to know because in real life, obviously there are some internal irreversibilities. And so you're never going to get to that 0.591 kilojoules, but it gives you a reference to see how good your real life situation is compared to the ideal situation. So it sets a benchmark that you can compare against, right? So that's convenient information to know. So in this example, I used the incompressible substance model for the soft drink, but we could also treat it as a compressed liquid and use the table. So that's what is done here. So we're assuming that the soda is a compressed liquid. So the change in entropy for the soda would be the mass times the change in specific entropy of the soda. The specific entropy of the soda, for a compressed liquid, recall that the entropy at some temperature and pressure for a compressed liquid is about equal to the entropy for the, I guess I've been using the symbol F, of the saturated liquid value at the same temperature. Right here, I apologize. Here I'm using a subscript L in the solution, but it's the same as the subscript F. It just means the saturated liquid. So that's what's being done here. That's why there's an approximate sign, is because the specific entropy for a compressed liquid is about the same as the specific entropy for the saturated liquid. And then as far as finding the specific entropies for the saturated liquid values, we can use tables. So in this particular write-up, I use the tables from Moran and Shapiro, your textbook. So the numbers look a little different from your Excel table, but we can look up the values. Again, the actual values aren't that critical. It's because we're taking the delta that's important. So if you looked in the Excel tables, I actually wrote this down. The saturated liquid value at 5 degrees C, it's a little different. It's 0.076254 kilojoules per kilogram Kelvin. You can see it's a little different from what I had from the Moran and Shapiro tables. And then if you use the 20 degrees C, it's 0.296480 kilojoules per kilogram Kelvin. So the numbers look slightly different just because they use different reference values. But in the end, if you use the tables, you get the delta for the soda, and it comes out to be virtually identical to what we used in the incompressible substance model. And the reason they're so close is because the temperature difference is very small here. It's only 15 degrees C, so the specific heat does not change very much over that range of temperatures. So you would expect that the change in entropy would be about the same. The last thing that I have here is actually a TS diagram. I haven't talked about TS diagrams in the lecture, but if you go back to the book style notes from the last lecture, I have a little bit in there about TS diagrams. These are used very frequently, just like PV diagrams and TV diagrams. And we're going to be using them extensively for the rest of the semester, so make sure you're familiar with them. But TS diagrams, just like the PV and TV diagrams, they just give us a graphical way to draw what cycles look like and to see what processes look like and such. So they look very similar to TV diagrams. In fact, you still have the vapor dome, and the isobars look the same as they would for a TV plot. I mean, again, these are just sketches. The real life picture looks much more skewed. But as far as our sketches, they look very similar to TV diagrams, except the horizontal axis here, of course, is specific entropy. So what I've done is I've drawn the isobars for the initial pressure and the final pressure. The final pressure turns out to be less than the initial pressure. You'll see that the reason for that in a moment. But we start with our initial state right here. We have our initial soda temperature and our initial specific entropy. It's a compressed liquid, so that's why I'm in the compressed liquid part of the diagram. So we're just off to the left of the vapor dome. And then we go to our final soda temperature, which is a smaller temperature. So we've moved down this way, because the initial soda temperature is 20 degrees C. Our final soda temperature is 5 degrees C. So we've moved down. And because we've drawn some heat out of our soda, the specific entropy of the soda has decreased. So now you see that we've gone from right to left in this picture because we've pulled some heat out, and we know from the entropy equation that the entropy is going to go down. Remember, we're dealing with an internally reversible process, so there is no entropy production. So that's our final state. So we draw our arrow there from the initial to final state. And it is also a compressed liquid. So that's why we're still in the compressed liquid region. And as far as the pressures, you can see that the pressure must go down. I've drawn the two different isobars. So we're actually on a different isobar, one that's lower than the initial pressure. So just graphically, we never did calculate the pressure in our example, but I know just from the graphical sketch here that the pressure must go down in our can of soda when we've cooled it down because of just the way it looks on the TS diagram. So again, get comfortable with drawing these TS diagrams in your problems because we're going to use them frequently, and they're just helpful to, like I showed here, I can immediately see what's going to happen to the pressure without actually doing any calculations. I can just see it graphically. Okay, so that's the end of this example. We'll do another one in a separate video.